And we're very pleased that we've been asked by STOA to participate in this large feasibility study effort with two technologies that we've seen through our global screening, one I'm presenting now and one in the afternoon. So we have come in as an independent consultant to validate the feasibility of these innovative technologies, put them through the diligence as prescribed by STOA. And well, the first one, the one I'm presenting now, is a company from Sweden, Pharem Biotech. The two gentlemen are also present here, so they'll be available for questions as well. Yeah, so for the background of this technology, it's an enzyme-based solution to break down micropollutants. And yeah, we will look at the details of it here. So the Pharem filtration system, you can imagine it as a basic sand filter unit with a sandy material with immobilized enzymes on this grainy material. These enzymes come from industrial productions, and they're specifically tailored in mixtures towards the micropollutants that are found in wastewater treatment streams. So clearly it is, in terms of process development, when you want to set up such a system, very important to select the right enzymes for the right for your wastewater. You need to make sure that these enzymes work at wastewater conditions, temperature-wise, pH-wise, and this is where the company has a lot of knowledge and a lot of experience. And then with having the right mix of enzymes, they're then immobilized to the filter medium and set up in such filtration columns, which gives a rather robust and scalable unit of post-treatment for wastewater. Here we have a look at a typical enzyme mix. On top here you have the different enzymes. Oh yeah, here we go. The different enzymes, some classifier names, and here a typical number of micropollutants that we want to degrade. So we can see that typically each enzyme is active on several of these micropollutants, and several of the micropollutants are attacked by various enzymes, which gives you a good certainty that these micropollutants will be broken down as long as the contact time is long enough. So by selecting the right mix of enzymes, you can, this is where a lot of the groundwork is focused on to be sure that the compounds are removed that you're looking for. So what have we done in this study? What was the general approach of doing this feasibility study? We have looked at a number of pilot tests that the company has done, as well as lab tests, and assessed them for the feasibility. We have estimated from that, pulled out the removal of the 11 indicator substances that we're interested in. And as one major design parameter, we are here in this feasibility study looked at an empty bed contact time of 5 minutes to do all the further calculations on energy demand, on lifetime of the medium. Then we have, of course, looked at the ecotoxicological effects of the output medium, how much toxicity would still be left. And what we can say here is that by selecting the right enzymes that attack the functional groups of these micropollutants, you can, upon further validation, this is an ongoing field of research clearly, but you can quite specifically say which bond should be broken down in the micropollutant, which is quite a large advantage to many of the other technologies out there. And then for this study specifically, we designed a 100,000 PE tertiary treatment step and looked at the CAPEX and the OPEX that we can expect from this, and then also, of course, the CO2 footprint to put it into the final analysis. And here's the results already. So we have in this session we're looking at a direct comparison to ozonation and sand filtration, since this is considered as the most advanced, more likely technology that you have to compare it with. In terms of the removal efficiency of the target micropollutants, this technology has come out about similar. There's not foolproof on all the 11 compounds that STOA is looking for. Some of these have simply not been tested yet. However, 7 of the 11 substances have been proven to be broken down with a certain enzyme mixture. What is quite interesting is the CO2 footprint. Since we're not looking at a carbon-based adsorption material, we don't have all that CO2 involved in the production of carbons. And since, well, the only energy demand that you have is a pumping, if not even the possibility of using just the hydraulic pressure that is there in the system to put the water through the sand filter. So your CO2 footprint would mainly come from transportation of the medium and from the production of the enzymes itself. These media, we estimate here in our calculations that they need to be replaced once per month in order to still have a high removal efficiency. And well, the same relates basically to the costs. There's not a lot of cost involved in energy demand, and the units themselves are rather on the low end for costs. So it's mainly the media replacement that is the driver here. But,
1 more minute, Bastian.
Perfect. Well, we're coming out favorably in this comparison. And in terms of ecotoxicity, this is something of ongoing research, but we can say from the evidence that we have so far that, there's a strong reduction in the ecotoxicity. And the next step, well, from our side, we would propose to have this technology tested and validated at a large scale in the Netherlands. We would want to look at the specific substances, of course, optimize an enzyme mix for the specific conditions, and really get first-hand validation of the CO2 footprint and the cost estimates that we've given here. And with this, I'm through with the presentation. Thank you very much for your attention, and we'll be around for questions as well.